the University of St Andrews. I would like to extend a warm greeting to all of our alumni, students, colleagues, and friends who are watching us from across the globe. My name is Craig Rutherford, and I'm a Development Officer for Arts and Divinity in our Development and Alumni team. If this is your first Saints Talk, then thank you for joining us. Our Saints Talks are short presentations by leading members of our academic community on key areas of our world-leading research. It's a little flavour of the expertise that our lucky students get to see on a daily basis. This evening's talk will be given by Professor Tom Kelsey from our School of Computer Science. And yes, you did hear that right. Professor Kelsey will, I am sure, be enlightening us on some of the ways in which computer science can help tackle cancer in a collaborative way. The talk will last for about 30 minutes, and then Tom will be happy to field your questions. We'll aim to wrap the event up by 6:15 at the latest, so do please get your questions in early during the talk if you would like to ask something. You can add questions to the chat bar on your screen, and you can do it at any point throughout the talk, so get them in early, and we'll try and get through as many of them as we can in the Q&A. Before we get into it, though, I'd just like to do a quick plug for the rest of our Saints Talk series. You can access the full archive of past talks on a range of subjects from artificial intelligence to marine mammal research on our dedicated St Andrews Alumni YouTube channel, where this talk will also be available over the coming days. And do please keep your eyes peeled for the next edition of Saints Talks, which will be advertised in all the usual places soon. Before that, though, let's get back to this evening's topic and tonight's guest. Professor Tom Kelsey is a researcher and data scientist in our School of Computer Science. Like many of us, he has a long-standing connection to the town, beginning his PhD in computational mathematics at the University of St Andrews in 1995. He's now Professor of Health Data Science and Scientific Director at the Wallace Kelsey Research Foundation. He also serves on the board of the NHS Scotland Managed Services Network for Children and Young People with Cancer. Professor Kelsey's primary research interest is the modelling of human fertility, working with data in collaboration with oncologists and fertility experts. He has a particular focus on assisted conception and oncofertility, a field that considers how to preserve the future fertility of patients undergoing cancer treatment. With long-term survivorships after cancer treatment improving in recent decades, it's increasingly important to understand the fertility deficit experienced by cancer survivors. In this talk, Professor Kelsey will explore the issue by presenting baseline models of fertility and demonstrating how they can be used to assess the impact of radio and chemotherapies. He will also discuss the safe and responsible use of these models and fertility preservation techniques before turning to the future direction of research and treatment. So without further ado, I'll hand you over to Tom for this evening's talk. Tom.
Thanks for the intro, and thanks very much for the invitation from Hannah and colleagues. The talk is about the structure. I'm going to talk about oncofertility, what that means, survivorship for cancer, incidence of survivor, the deficit of fertility for cancer survivors. Look at some baseline models for ovarian reserve and biomarkers for the ovarian reserve. Brief word about external validation, how the models are used, and how we think they should be used. This is appropriate use of the models, and then talk a bit about what's happening currently and in the future. So oncofertility isn't a word in a dictionary. It's a portmanteau word coined by Teresa Woodruff when she was at Northwestern in 2007. So it's oncology and fertility, bridging oncology and reproductive medicine to address the infertility risk caused by cancer treatments. Because it's specialized and interdisciplinary, you need at least two areas of expertise. So all the work I'm describing involves Richard Anderson, who's a reproductive medicine expert, and Hamish Wallace, a pediatric oncologist, both from the University of Edinburgh and various hospitals in Lothian. So these are practicing consultant physicians who have a keen interest in the late effects of cancer treatment, and specifically the late effects of cancer treatment on fertility. First, we want to establish that there are risks, and second, that this is a growing problem. This is a real problem for society to address. So this is the most recent data from the Scottish Cancer Registry. This is observed survival in children, 5-year survival across common cancers, or most of the cancers. And the news is fantastic. You're seeing 5-year survival rates in the 80%, 90%, approaching 100%. Lymphoid leukemias, incredible work's been done in recent years to cure cancers. So people will present with a cancer and they can expect to be cured. This is the same data, but for young people. And again, survival for germ cell tumours, skin cancers approaching 100%. There are still areas where things can be improved, like bone tumours. But in recent decades, or in the past few decades, cancer treatment has improved dramatically. What this means, so this is more population data, but this is for the United States from their NCI. By 2035, they expect 22.5 million US citizens to be survivors of cancer. They estimate that it was getting on for 19 million in May last year. So that's 1 in 20 of the US population are survivors of cancer. And so this establishes that it's a real issue. You want to be cured, obviously. You have a diagnosis of cancer. Cure is important. But the treatment for cancer, or the treatments for cancer, can have severe effects on learning difficulties, growth, fertility, psychosocial issues, and in our opinion, should be addressed. To show that there's a fertility deficit, here's one of our papers from 2022. This is based on the entire population of Scotland, female population of Scotland, for these data. So the hazard ratio, if the hazard ratio is 1, there's no deficit. And so for leukemias, only 30% of female survivors of leukemia go on to have a live birth. It's a bit better for things like Hodgkin lymphoma, but for all diagnoses, between 50 and 60%, 55 and 60% of the people expected to go and have a live birth actually go and have a live birth if they have survived cancer. So there's a real deficit. There's a real growing population of people whose fertility may or may not have been compromised by the treatment, and for whom help is needed. So when we started this, we found that the oncologists, they've got excellent cancer registries, survival data, clinical trial data, everything else. And we wanted to assess the damage done by chemotherapies, radiotherapies. But in reproductive medicine, there was a deficit of holistic models, and by holistic, I mean from conception to old age, for the human ovarian reserve and key endocrine physiological indicators of ovarian reserve. And so our problem starting off is that we didn't have good estimates of what happens to someone with 0 cancer treatment. We need a baseline model from which to adjust to see how far away a cancer survivor is from normal fertility. So I'm going to present 5 of these. They've all got similar methodology. a lot of work is to find all the reported data from healthy subjects in the literature. Extract these data from scatter plots or synthesize from descriptive stats. Force the data to go through zero at conception. So for all of these things, the only thing we know is that they're zero at conception. And then find and agree upon a model and report a model, publish a model that we hope best explains the trend and the variance in the combined data. And so these will give an average and a range for these indicators of ovarian reserve. When I talk about ovarian reserve, it's the number of cells in the ovaries that can mature into eggs. These are known as oocytes or non-growing follicles. So in the ovary, these cells can be recruited towards maturation. Very few turn into eggs, but the reserve is the number you've got. When the number goes below about 800, there's not enough to be recruited. The ovaries stop producing eggs, and the woman is menopausal. We don't have any technologies for directly measuring ovarian reserve. It's all done by sampling and slicing ovarian tissue and counting and then integrating. AMH and ovarian volume are indirect biomarkers of ovarian reserve, commonly used. Inhibin B is a biomarker for fertility in males, and testosterone is a definitive biomarker for male fertility. So here's the ovarian reserve. The thing not to look at too closely on this slide is the shape of the curve, because everything's been log adjusted. I'll show in a minute what the curve actually looks like in real terms, as it were, in untransformed terms. The main thing to get across is that we can, or we could, find enough data to show the growth from no ovarian reserve to the peak that happens halfway through pregnancy and the later decline towards menopause at around 50, 51, 52 years. And the key thing is there's a huge range. So the average might be the red line, but there's a huge range either side of that for normal ovarian reserve. What this means for girls and women is that they're born with nearly 100% of their ovarian reserve. Cells are lost, so the ovary is active in prepubertal years. There's 36% left normally at age 20, 12% at age 30, only 3% left at age 40, and by age 50 typically there's diminished ovarian reserve, and therefore no eggs are being produced, and there can't be any live births. And so this line, or these lines on these charts, this is what we adjust from. If we found a cancer survivor had 20% at age 15, then that's diminished ovarian reserve, and she would likely to be have premature ovarian insufficiency and be menopausal much earlier than age 50. AMH, again, you can see there's a very wide range. We collected a huge amount of data, did some intensive modeling to come up with a baseline model, plus the variance not shown on this slide, some other analyses. But this gives us a normal AMH, age-related, from conception to age 51. Again, huge amount of variance. Ovarian volume is something that can be measured by ultrasound. This starts off at 0, grows until about age 20, and then there's a decline up until to postmenopausal ages. So again, we've collected a huge amounts of data from studies published all over the world, found the best model that describes the average and the variance at all ages. Testosterone, same thing, combine huge number of data points, not from conception here, from age about 3.5, but all the way up to age 88. And we can show what's happening in prepubertal, pubertal, and then adult males. And this gives us normal ranges to assess, as before, the damage done by radio or chemotherapy. Inhibin B, restricted age group, so 0 to 17 years. But again, we collect all the data and we come up with a predictive model that we can use to assess how much damage has been done or how little damage has been done by any given combination of cancer treatments. So we published the model. The models involved all the data we could find, and we searched high and low at that time. But what we really want is external validation, which is the gold standard for a data science like myself. So we derived and assessed them using all the data available. We used various techniques to internally validate the models to make sure that they conformed as well as possible to the available data. But the true test of one of these models is what happens when new data comes in and you make predictions using the model and you compare those to the new observations. If they match to within the various established by the models, then you've got external validation. And that model is then suitable, or you can carry on using it for clinical use and investigations. If not, however, your model was deficient and it's not suitable for future use, and it's consigned to the scrap heap of history, and you start all over again. It turns out that all of these models that I've presented have been externally validated, either formally or in the sense that they're still being used today. Nobody has come along and said, no, this model doesn't describe what happens to testosterone or inhibin B or whatever. To give a direct example of external validation, we calculated the mean follicle density for healthy females. We made the assumption that a large ovary contains more eggs than a small one. We used our ovarian reserve model that gives us ovarian reserve NGFs at a given age, at a known age. We use our ovarian volume model. We then combine those, making some adjustments for the structure of the ovary, compare predictions to new histology lab observations that we didn't use to derive either model. And good alignment shows external validation for both the ovarian volume model and the NGF model. So to do this, ovarian tissue is taken from healthy survivor and cancer survivors. It's sliced, it's stained, and then people count, assess the actual density of follicles in that ovary. And we found that if we did that, if we combined observed to predicted, we were in very good agreement. Despite all the huge variation in volume and NGF, if you combine those models, you agree fairly well or very well with what you see for new data. External validation is typically not done by me because marking your own homework is not good practice. I'm biased. I would like my models to be externally validated, and so it's not seen as a good thing to go around claiming that you've externally validated your own model. I am sometimes involved. So currently, last week and this week, Scandinavian researchers have got inhibin B data from children and young adults after bone marrow transplant, and they want to compare their data to our published normal ranges. And so I'm working with them on that to establish the gap, or if there is a gap, or the size of the gap between the inhibin B for the cancer survivors and the normal population to establish the damage done by the treatment leading to the bone marrow transplant. So to use the models, we'll start off with radiotherapy and then move to chemotherapy. So background for radiotherapy, we published an assessment of the radiosensitivity of the human oocyte back in 2003. So for radiation, the LD50 is the amount of radiation needed on average to kill half the cells. So there's an LD50 for lung cells, brain cells, liver cells. Radiology is more or less the art and the science of designing treatments that kill cancer cells, but do not do too much damage to the other important cells in other important organs or parts of the body. And so every organ's got an LD50, and we established the LD50 for the human, for cells in the human ovary. We use that to predict ovarian failure after radiation for a given dose. And then we've got a tool. We developed a predictive tool. If you input the age and your planned dose to the ovaries, then you will return a window of fertility after treatment. So this is specific use. And this makes a difference. So this is data from, these are plans from Florida in the USA, our colleagues from there. They have got the same subject with the same cancer. They've got proton therapy and they've got photon therapy, two different types of radiotherapy. One of these does more damage to the ovary than the other in terms of radiation received. So the photon plan, according to the calculator, will mean that this child will be infertile, expected to be infertile at age 21, plus or minus confidence interval given by the tool. But the proton plan delays that infertility by 12 years. And this sort of motivates a choice for the family, for the girl herself. Once she survived, hopefully, and in all likelihood will survive, for the proton plan, in the absence of anything else, then she should try and start a family much younger. For the photon plan, it may be that some ovarian tissue should be cryopreserved to help to retain some future fertility. For chemotherapy, we can observe, this is mean follicle density before and after treatment for different chemotherapy regimes. So the blue points on here are our predictions for normal people, normal meaning not cancer survivors, the absence of any chemotherapy. And again, model is predicting very well. And this shows that ABVD chemotherapy has a different effect to COPDAC chemotherapy. So I'm not an oncologist. I don't know what these chemotherapies do, but they have a measurable and general and predictable effect on the ovarian reserve. And so again, we can use that to take into account the likely damage that the treatment is going to do, and use that to counsel and to plan for later fertility. For risk assessment, a lot of oncofertility is trying to identify those most likely to benefit from emerging treatments and technologies. So this is diagnostic and predictive accuracy of AMH for ovarian function, adult women with early breast cancer. And so we can use pre-treatment AMH some other baseline data, and 3 months post-treatment AMH to predict infertility later. That's the red curve. And the difference is there are two different definitions of infertility. But what this shows is that using AMH and using our model for AMH reliably discriminates high and low risk of later infertility. So 3 months after treatment, you can be fairly sure whether you do or you don't need to modify your hormone, later hormone treatment for the breast cancer survivor to take fertility into account. So this leads to responsible use of the models. So hopefully I've established or have shown that we can help with treatment planning, and we can identify those most at risk and therefore those most likely to benefit from fertility preservation techniques, which I haven't spoken about, so I'll fill that gap here. It is possible. When I started doing this, it wasn't possible to do this. This was science fiction. But in the last 10, 15 years, a huge amount of work's been done on here, and it's been very successful. So it is possible to take an entire ovary or slices from the cortex of an ovary before treatment, so before the radiotherapy does the damage, before the chemotherapy does the damage. You remove this tissue, cryopreserve it. It stays in cryopreservation, waiting until the survivor is thinking about starting a family. It can then be reimplanted and incredibly revascularized. So this frozen tissue can be reimplanted. A blood supply will connect it to the hormones needed for it to turn into real working ovarian tissue. And that means mature eggs can be harvested from this tissue, and those mature eggs can be taken and fertilized, typically using IVF, using assisted conception techniques. And this has led to, so now there have been more than 200 live births worldwide. So this generates clear questions. So should this be offered to very few and concentrate on curing the cancer? So the standard oncology approach to this is it doesn't really matter if the survivors can have families or not. The most important thing is the cancer is cured and it doesn't come back. And so it may be that if we give him a huge dose of radiotherapy, you could do this, but in general, you wouldn't do it. There are countries like Denmark where if you're diagnosed with breast cancer, they will offer this to you. They offer it to everyone. So there's a huge amount of tissue being stored in Denmark and other countries, waiting for the survivor, hopefully to decide that they want to start a family. There's a sort of an interim place where we identify those most at risk of later infertility and offer only to them, which is what happens in Scotland. So some countries, oncofertility, nobody cares about it. Others, it is absolutely core, and better be safe than sorry. We cryopreserve for everyone. And there are other countries like Scotland where we try and do things properly, in my opinion. So this again is population. This is all of Scotland. Analysis of criteria for ovarian cryopreservation. So what will happen is you will be offered or not offered based on set criteria. I'm not going to go into those in any detail. And so we've got data on this, and we know what happens. We can follow them up. We can go through the medical records. Well, I can't go through any medical records. I just analyze the data. And the question is, do the offered group have a higher prevalence of later infertility? If they do, then we're on the right lines. And we see from our Lancet Oncology paper that this is true. This is what's happened. If we offered cryopreservation, or the patients who were offered cryopreservation were much more likely to have premature ovarian insufficiency compared to the not offered. We did that again. 15 years sounds like a long time of follow-up, but these are small numbers. So we did it for 20 to 25 years follow-up, and repeated the analysis just to make sure that those trends continued, and they do. So we published this a couple of years ago. There are two different populations: the ones offered and one not offered. And it looks like that the ones who are being offered are the ones who genuinely are the ones most likely to benefit. Future work. This is still, so I've shown a lot of results from more than 20 years ago, up until sort of recent publications. There's still a lot of activity here. Most of the data isn't longitudinal. So I typically have data from healthy subjects, or I have data from cancer survivors, and it's very rare that they're the same individuals. So the modeling is groping in the dark to a certain extent. We haven't followed people for 3, 4, 5 years to see what actually happens after a known treatment. So to get around this, we've got the PROTECT study funded by the Medical Research Council and the EU now, and we're trying to address this. So we now have over 500 children and young adults diagnosed with cancer at 35 UK centres. We know their baseline data in terms of things like ovarian volume, AMH, inhibin B, testosterone, everything else. So we've got all the biomarkers before treatment started. We know how old they are. Obviously, we've got BMI and all the other baseline data. We know what treatment they had, and when they had it, and in what combination. And each of these subjects comes in and gives us follow-up data at sort of 1 year, 2 year, 3 year intervals. The plan was for 3 years follow-up, but that's been extended to 5 years because this is looking very promising. And the longer we follow up, the more information or the better analysis of trends we can do. And the idea is that these data will allow us to solve or partially solve the issue of not having longitudinal long-term follow-up data that has restricted our ability to produce results in the past, or we still produce them, but it's compromised to a certain extent their strength. So these data will allow us to improve our models, inform treatment planning. This is the whole idea. What we want is treatment to be planned so that it minimizes damage to later fertility. And also enhance fertility counselling. We think it's very important that later fertility should be part of the conversation before treatment starts for everyone diagnosed with cancer. If, as we all hope and expect for certain cancers, that you're going to be alive for a long time after surviving this cancer and having the treatment, there's a counselling about what can be offered, what should be offered. Do you need to worry? How much do you need to worry? And so on. So that's the summary. Thanks for listening. And has anyone got any questions?
Thanks very much, Tom. That was really great. I'm always amazed that it's genuinely enlightening and interesting to see the research of all of our academics here at St Andrews, and I think we can all agree that that's really important research that you're doing, and that's evident in some of the questions that are coming through. So for people that are watching, if you have questions and you haven't asked them already, please do get them into the chat bar so that we can get asking Professor Kelsey some of these important questions. But firstly, I was going to ask you myself. You were talking about collaborators in Edinburgh and having data for all the kind of female cancer cases in Scotland. Is Scotland or the UK as a whole a particularly good joined up place to do your kind of like data-led health research? Is there anything better here than other places, or is it hard even to do that work across international borders, like with the UK, if that's something that you also do?
That's a good question. It's Scotland is better than most countries. Scotland is better than nearly all countries in this respect. So in Scotland, everyone who interacts with NHS Scotland gets something called a CHI number. It's a Community Health Index number. We've all got one. Sorry, you and I have got one, and I'm not sure where everyone else who's listening to this is. So you won't have one of these if you're in England or Wales or France or anywhere else, right? And what this means is that Public Health Scotland, so I ask for all of the cancer registry data, and I want it linked to the mental health records, the prescribing data, maternity, day case, and they can link these very easily. So I've got all the data for everyone with cancer in Scotland, and everything else that's happened to them in terms of mental health, fertility, and so on. And then they can link them by age and where they live and income and stuff like that, and provide data sets which cover all of Scotland, the entire population. There can't be any selection bias. And Public Health Scotland can do this really easily because they can automatically link it, whereas that's much, much harder outside Scotland.
Very interesting. Thanks. And do you work across international borders as well, or are you collaborating within the UK just? Or?
So I do a lot of work in assisted. So everything that I've shown is interesting to people who do assisted conception, IVF.
Yeah.
So I do a lot of work on that as well, which I didn't mention in this talk. So I've got collaborators all over the world for that. But in terms of oncofertility, we work with people in Denmark, Sweden. We work with people in the United States. It's a very big thing in the United States. In the US, children with cancer pretty much all go to the same hospital, or their treatment comes from the same hospital in Memphis, Tennessee, and they've got a very firm interest in late effects. So we collaborate with them, but also with researchers in South Africa recently, Australia. We're doing a lot of work with those.
Right. It's really great to see St Andrews doing this kind of stuff all over the world. It's amazing the kind of effects that we can have whilst we're a small institution in the northeast of Fife. But it's great to see. I was going to ask as well, should we be investigating these kind of late effects of cancer at all when there's so much pressure on the initial treatment of cancer and the kind of primary risk of cancer? Is this something that there's a strong argument for?
There are many oncologists and hematologists all over the world. In fact, many, quite possibly a majority, who if they listen to this talk, would say, let's forget about all this. My job as an oncologist, hematologist, is to cure the cancer. Mm-hmm. And if the survivor has got learning difficulties, growth, or fertility, then that's not a problem. all of the focus on cancer should be on treatment. And it's that sort of blinkered and focused thing that has led to the massive increase in survival rates, for which the oncologists and hematologists should be commended. It's amazing what they've done. But because they've been so successful, there is now a growing population, and of course, childhood cancers and young adults, they're going to last. They're going to live longer, hopefully. It seems obvious to me that there's a growing number of people in society who are cancer survivors, and their survivorship should be something that is of interest and taken into account by the NHS and by the clinicians they encounter and deal with.
Thank you. I'm going to turn to some of our great viewers' questions that are coming through now. I've got one from an anonymous questioner who says that you mentioned that there's low percentages of live births for females across Scotland who have had cancer. And did these numbers include those who may have had fertility treatment as part of their cancer treatment?
Had fertility treatment as part of their cancer treatment? I'm not sure.
Is that... I'm reading out a question that's come in verbatim. So is there...
I don't know. Right. No, I think it includes those, right? Whatever that means, okay. It includes them because this is population data, right? So you're either in the cancer registry or you're not. Okay. And for those in the cancer registry, whatever happened to them, whatever treatment they got, and whether they had any fertility-related stuff during treatment, that's taken into account in the deficit. So if you were diagnosed with that cancer, then this is the gap, this is the deficit between you and the healthy population who in terms of expected live births.
Thank you very much. You mentioned quite a lot as well. There was mention of the kind of treatments that you can do pre-cancer treatment in terms of freezing eggs or freezing ovarian tissue, which I'd never heard of, which is absolutely amazing that they can do that kind of stuff. Offering that, and you said it's offered in other countries. Is this something that is happening in the UK or should be happening more in the UK?
It's patchy, right? It's not offered throughout the UK. So in Scotland, if you have a diagnosis, then you will be assessed using our criteria, which we think have been validated, to whether you should be offered cryopreservation, yes or no. Yeah. And so it does happen in Scotland, and it's happening more often with boys in Scotland. So there's a keen interest in Scotland. There are groups in Oxford and London that do this as well, but this isn't something that the NHS for the UK has considered important enough or established enough to roll out, as it were, for everyone.
Yeah, thank you. I'm going to ask you a specific question that one of our viewers has put in about chemotherapy, which may or may not be within your expertise, but they're saying there was a slide showing effects of different chemotherapies on female fertility.
Yes.
Could you explain a bit more about the detail, what the data shows about the effects of ABVD chemotherapy?
Okay, ABVD. I think the V stands for vincristine. So, okay, I'm going to say a bit more about chemotherapy in general, right? So
yeah, that'd be great.
There are some chemotherapies that we don't think do much damage at all to ovarian tissue. Platinum-based ones, things like cisplatin, are known to be toxic to ovarian cells. So we've got a hierarchy of what we think the damage does for each drug. So ABVD each stands for, so essentially what you do is you get a cocktail. You get A, you get B, you get V, and you get D, whatever they are, right? And of course, the cocktails change with clinical trials. So there'll be a gold standard, but then they'll introduce or different rates or a different order for these things. And this muddies the water for us. So we're trying to find the damage done by each protocol. And so it's very difficult. So it's very rare that anyone gets just one chemotherapy drug, which makes it very difficult for us to tease out how much damage that drug did, specific drug, did to fertility. So this is something that the Americans, so Teresa Woodruff and her colleagues, huge amount of work on this. We're working on this now. The idea is to enable the counselling. So you are getting, we think, to increase your chances of survival, you should be getting this chemotherapy, but this is known to do a large amount of damage, or a small amount of damage, or a medium amount of damage to your fertility. What do you want to do about cryopreservation, if anything?
Thank you. Another one of our viewers, Jocelyn, has asked, do you expect the prediction landscape to change with the development of immunotherapies, and I guess with any other new therapies that might be coming through in terms of cancer?
Yes, right. So it used to be pretty easy, right? Cancer treatment was a large or a small amount of radiotherapy, or a small number of chemotherapies. There are new therapies coming in. So the immunotherapies that affect the immune system to try and discourage the growth or the establishment of cancer cells. Do these. So what we'd have to do is we'd have to look at the fertility of MS survivors, people who routinely have immunotherapy, and see if there's anything there that would help as that transfers towards cancer treatment. But we haven't looked at that yet.
Thank you. And I've got one final question for you. I'm going to ask a kind of wider question, because I know St Andrews has a lot of expertise in AI, and I was just wondering whether you think that kind of new AI technologies and different applications of it can be helpful in this kind of predictive analytics that you're working on.
Right. So I do a lot of work on new AI because I'm working in computer science at St Andrews. In terms of general fertility, the answer is yes. So in assisted conception, in IVF, where we have much more data, there are many more couples trying to have a family using assisted conceptions than there are people with cancer. And so we've got much more data on assisted conception cycles and so on. And AI, I think I published something last month or in January about this. So we are actively working on this, and we think we're making a very good progress on this. For oncology, it's less likely because numbers are very small. And modern AI, in order to train it and use it, you need a lot of data, and ideally a lot of high quality data. And typically for oncology, we don't have that. It's still, you're very unlikely to be diagnosed with cancer as a child or a young adult. And then you've got the subdivisions by the cancer, then you've got the subdivisions by the treatment, and so on and so forth. So we're not there yet. We do think that AI is very important in fertility, but at the assisted conception stage in early 2026.
Brilliant. Thank you very much. I'm going to wrap up there because we're just about out of time, but it just falls to me now to thank you very much profusely again for taking the time to speak with us and to kind of share your expertise with us. It's really great to spend time with our leading researchers when we can. So thanks also to the staff who've given their time to make arrangements for this event. And there's a lot of work that goes into these, and it's very much appreciated by all of us. But finally, it's a really big thank you to you, our watchers and our esteemed alumni and students and staff and friends who attend these talks. We're really delighted and pleased to be able to welcome you virtually back to St Andrews every few weeks. So please do continue to attend these events. And as I said, please keep your eyes open for notice of the next Saints talk soon. We look forward to seeing you then. But for now, thanks very much for joining us and enjoy the rest of your evening.